All right, so last section we're going to look at is 11.3. It's called the Binomial Theorem. And we're going to start by looking at a sum, okay, two things added together. But we're going to take a sum and raise it to a power. So I want to start with a plus b squared. What do you get when you square the sum a plus b? How about 8? What do you get when you square that?
A plus b squared.
Well, what does that mean when you have that exponent of
like
2?
The full rate math thing. I'm way too tired to answer that question today, man.
All right. Can anybody help him out? How do you square a plus b? Yeah.
You use FOIL of a plus b and a plus b, so you get a squared plus ab plus b squared.
So you do have to FOIL it out. You're close, not quite. Yep.
A squared plus 2ab plus b squared.
Right. A squared plus 2ab plus b squared. Okay, so that's what you get when you do that up. Okay. Now let's do a plus b cubed. So that means to take a plus b squared, which we already did out, and multiply it by a plus b again. So, okay, so multiply it by a plus b. And now we have to distribute it, so we have 6 multiplications this time. So distribute a to everything. And then Kyle, when I distribute a out, what's that going to give me?
A cubed plus 2a squared b plus e squared a.
Yeah, I'm just going to keep everything in alphabetical order, so I'm going to write it as ab squared. Okay, and now we have to distribute the b to everything. If we have any like terms, we'll put it all together. Sarah, what do I get when I distribute b to everything? So yep, an a squared b. And I see some other a squared b, so we'll be combining those in a little bit. Yep, keep going. So then 2ab squared. Yep. And b cubed. So let's combine the like terms. So we've got 2a squared b, 1a squared b. So that's going to give me 3a squared b's. And then I have 1ab squared, 2ab squared. So that's also going to give me 3 of those. So I'm going to have a cubed and b cubed on the ends. And in the middle, I'm going to have a 3 for the a squared b's and another 3 for the ab squareds. So that's going to look like that. So now I want to look at a plus b to the 4th. So we'd have to multiply it by a plus b again. Well, the problem is it's going to start getting longer and longer. Right? So we're going to need a quicker way than to keep multiplying a plus b over and over. Okay? When you do it to the 4th power, you're going to get that. And when you do it to the 5th power, you get that. So the goal is to try to look at that and see if we can notice any kind of patterns. Looking at the expansions of all those sums raised to a power. So these are all series. They're all a finite series. You're adding a bunch of terms together. But it's not an infinite amount. Okay, we're not doing anything with infinite amounts. But looking at the different expansions, does anybody notice any patterns? Yeah.
That like the larger exponents on the outside.
The larger exponent is on the outside. What do you mean?
So like it goes 5, 4, 3, 2, 3, 4, 5. So they go like it's like I don't know if that's just how you like wrote it. I don't know if it matters, but
So yeah, let's talk more about the exponent. So what do you notice about the exponent?
Like the larger exponents are on the outside, and then it gets smaller as it gets to the middle.
Okay, so let's focus on the exponent on just a. So what's happening there?
Oh, it gets smaller from left to right. So it's 5, 4, 3, 2, 1, and then 0.
And then it's gone, right? So we have every power on a, starting with the highest power, going all the way down to the lowest, and eventually it's gone. So the exponents on a are decreasing by 1 each time. How about the exponents on b? Yeah?
It's increasing from left to right.
Yeah. So we start without an exponent in b, and then we start with b to the first, b to the second, third, fourth, and fifth. So the exponent on the b is going up each time. Anything else you notice about the exponents? So the pattern of increasing and decreasing, that's important. Something else, yeah?
I'm not sure, but for every, so if you have like an exponent of 4, you have 5 terms. And if you have like an exponent of 3, you have 4 terms.
Yep, so this exponent is basically, if you add 1 to it, it tells you how many terms you'll have in the expansion. So when you cube something, you're going to get 4 terms. When you square, you get 3. Raised to the 4th power, you get 5 terms. Yep. So there's always 1 more term in the expansion than the exponent. And if you look at the sum of the exponents in any term, what do the sum of the exponents always add up to? Yeah? In this one, it's 5. But in general, they add up to the power that you had originally. Yep. So all the exponents in this expansion are going to add up to 4. 4, 3 plus 1, 2 plus 2, 1 plus 3, and then a 4. So the exponents always add up to this number. Something else we haven't talked about yet, but we need to be able to figure these out too. What else is in the expansion? Yeah?
Is it a Pascal triangle?
Yeah, Pascal's triangle. So we talked a little about Pascal's triangle earlier. I'm going to come back to this slide, but earlier in the week. And told you the numbers are used for lots of different things. But one thing we can use them for here is to help us find coefficients. So look at row 3 and look at the numbers in row 3. 1, 3, 3, 1. Go back to where we cubed something. Cubed. 1, 3, 3, 1. So to figure out the numbers that are in front, 1, 4, 6, 4, 1, we can use Pascal's triangle to figure them out. 1, 4, 6, 4, 1. Now, if the row starts to get really high, unless you have Pascal's triangle already done out, like if you raise something to the 50th power, well, using this triangle would work, but it's not going to be practical. So maybe up to like 7 or 8 rows, you should be able to generate pretty quickly. Beyond that, we're going to have to look at a different way to do it. But yes, the numbers in the expansion are all found in Pascal's triangle. So I think those are all the patterns. We said this one. Each expression has 1 more term than the power. The sum of the exponents always adds up to the power. That was the first thing we said. The exponent on A was going down by 1, B was going up by 1. And the last thing we figured out, where are the coefficients in the triangle? Where are they coming from? They are coming from Pascal's triangle. So now we've got a quick way of taking a binomial and raising it to a power without having to FOIL the whole thing out. So just going to practice doing a few of these out with Pascal's triangle, using Pascal's triangle and the patterns that we just noticed. Okay, so I've written Pascal's triangle out for the first few rows. I already showed this to you earlier in the week. But you always start with row 0, and then column-wise, you also start with column 0. So like that number that I just circled, that is row 6, column 1. This is column 0, column 1, 2, 3, 4, 5, 6. If you don't start with row 0, column 0, it's going to mess things up. So always start the way it's labeled there. In the triangle, each row begins and ends with a 1, and each number is the sum of the two that are directly above it. 4 plus 6 is 10, 5 plus 10 is 15, and so on. So let's try a few expansions, okay, doing out a binomial raised to a power. And we'll start with a pretty basic one. We'll just start with two very simple terms inside a and b. And we're going to raise it to the 6th power. Okay, so let's start with our coefficients. The coefficients are going to be found right there. That is row 6. Okay, we go into the 6th power, we need the 6th row. Emma, what's my first coefficient in row 6 of Pascal's triangle? 1. Okay, 1 is the first number in every row of Pascal's triangle. So we're always going to start with a 1. And now, keeping in mind the patterns, we're going to start with the a variable and put the power, the b variable, put the power, and then go to the next term. So what would be the power on a in the first term? Yeah, 6. So you're going to start with a to the 6th. What would be the power on the b in this term? Yeah? There is a power. Every letter has to have some number on it. Yeah. 0. So it's to the 0 power, but because it's to the 0 power, it's just going to multiply by 1, so we don't have to write it. Okay. That's your first term in the expansion. Okay. My next term. Davis, what's going to be the coefficient of the second term in this expansion?
6.
It's going to be a 6. Yep. So 6. Now I need a to the power. Jacob, what's going to be the power on a? 5. So a to the 5th. And Alex, how about my power on b?
1. Power of 1.
Yep, it's going to be b to the 1st. Okay, so we're not really doing any math here. We're really just following a pattern to expand it out, rather than having to do all the foiling, which would take a long time. Okay, how about Kylie? Do you think you could give me my entire next term?
15a to the 4th b squared.
15a to the 4th b squared. Yep. Dan, my next term?
20 a to the 3rd, b to the 3rd.
Yep. 20 a cubed b cubed. Plus? Yes. Yeah, just sign out and you're all set. Thank you.
Where did I sign up?
Just do other. Okay, 20 a cubed b cubed looks good. Now we've hit the highest coefficient. We're in the middle. Now we're going to go back down. Okay. How about the next term? Anyone think they can give me that one? Yeah. Nick?
15a squared b to the 4th.
Squared b to the 4th. Hadley, could you give me the next one?
Would it be plus 6? No, b to the 6th. Or is it?
The 6 is good. We definitely want that.
6ab the fifth.
Fifth, yep. So 6ab to the fifth. And Eileen, how about my last term?
B to the sixth.
Yeah, it's just b to the sixth. There's a 1 in front of it, but that doesn't do anything. So that is the expansion. And that is a lot faster than trying to do a plus b 6 times in parentheses and FOIL it all out. And once you get the pattern, I mean, you really can go through it pretty fast. You just have to know the triangle you need, what row, and then make sure you start with your first variable, highest power. That one goes down. And then on the other variable, the power goes up. Okay, let's try this one. 2x plus y to the fourth. Okay, so we need the fourth row in Pascal's triangle. Aiden, what's the fourth row in Pascal's triangle?
One second. 1, 3, 3, 1.
1, 3, 3, 1. So I think that's your third row. We need one more.
Oh, you said 4. Sorry.
Fourth row. So the row we're looking for always has one more number in it than the exponent. So it has 5 numbers.
1, 4, 6, 4.
1, 4, 6, 4, 1. So there's our coefficients we need to use. 1, 4, 6, 4, 1. So let's start with the 1. What's going to go next to the 1? Yep.
2x to the fourth.
Right. This whole thing is like our A. That is like our B. So we do the first thing in the parentheses. That goes to the highest power. And what's the power on y in this one? Yep.
0.
0. Why we don't need y yet. Okay. Next term. Julia, what's my coefficient going to be?
It's going to be 4.
4. Yep. And what's going to go next to it?
2x to the third.
Yep. This whole thing now to the third, and then next to that,
Y to the first.
y to the first. Okay, so that's our second term. Jace, how about my third term? Start with, what's my coefficient going to be?
I was so zoned out.
Anyone help him out? What's our coefficient? Yep.
6.
6, coming from that row in Pascal's triangle. 6. Okay. What's going to go next to 6? Yeah.
2x squared and y squared.
2x squared. And remember, these two x's to powers, they all have to be done out. Okay, so we're not doing them out right now. We're just trying to get them written. Then we'll do them out. Okay, so that's our third term. Second to last term. Anyone think they can give you that one?
Shouldn't it be 2x squared y squared? Okay, and then the next one would be 4 2x and y cubed.
4 times 2xy cubed. That's just 2x to the first. You don't have to write to the first. Okay, and what about the last term? Yeah,
Y.
just y to the fourth. Okay, now because these terms here had 2 factors in it, we have to do those out. Okay? So let's do out 2x to the fourth. What do you get when you raise 2x to the fourth power? Yep.
16x to the fourth.
16x to the fourth, and then times 1,
16x to the fourth.
still 16x to the fourth. Okay. So these coefficients are not going to end up being in the final answer, obviously, because they're going to get kind of hidden. They won't be obvious anymore. We're going to be multiplying them by numbers. Okay. How about the next one? What's 2x cubed? Cube 2x, Nick?
8x cubed.
So 8x cubed and then times 4.
32x cubed.
So that's 32x cubed y. So that's your second term. Okay, how about my third term? Anyone think they can give me that one? Yep.
24x squared y squared.
24x squared y squared. Good. Okay, how about my fourth term?
8xy cubed.
8xy cubed. And the last term is done. Okay, so I did a little bit of work at the end because we had to simplify everything that was raised to a power, but that's how you have to do it. It was more work, so I didn't have it as high of a power as the last one. Any question on that one? All right, and let's try this one. So we'll do one more, a little bit lower power, 3x minus 2y cubed. Okay, what are the numbers we need from Pascal's triangle? Yep,
1, 3, 3, 1.
we need a 1, 3, 3, 1. Yep. Okay. So first coefficient is going to be a 1. Then it's going to be 3x cubed. And then the negative 2y we don't need yet because that's to the 0 power. Okay. How about my next term? Anyone? You don't have to do it. There's going to be a little bit of work to do out, but let's get it written with the powers, then we'll do it out. Yep.
3 times 3x squared minus 2y.
So the term, this is just a term. We don't want to create two terms here.
Oh, yeah.
You just want a single term.
2y
And what would be?
to the first one.
So times negative 2y to the first. Okay. Hunter, how about my next one?
Your end one should be negative 2y cubed.
I'm sorry, next one.
It should be 3 and 3x parentheses 2 or negative 2y squared parentheses.
2y squared, because that's to the first. All right, and now we're down to the last term. This one's always, the first one and the last one are always the simplest because they don't have both variables in them. So Reese, what would my last term be?
Negative 2y cubed.
Negative 2y cubed. Okay, so do the first one out. Lucas, what's 1 times 3x cubed?
27x cubed.
Good. 27x cubed. You don't have to worry about anything with y yet. Okay, so we don't have the y. Alex, let's do the next one. What's 3x squared? And you know what? Let's just do the number for now. Let's come back to the letter. So 3 squared, and then times 3, 27, and then times negative 2.
Negative 54.
All right, so that's our coefficient. It's a negative 54. First time we've seen a negative, and that's because of this. That was a negative. And then what about your variables?
X squared and y.
Yep. So it's probably easier to think about the variables after and then just do the number part first. Okay, next one. How about Maggie? What's 3x to the first? 3? Yeah, I'm sorry. Let's just do the 3. So 3 to the first is 3 times 3, 9, and then times negative 2. Well, actually, let me change that. 9 times negative 2 squared. And what kind of 36 is it? Well, negative 2 squared is how much?
Oh,
4
so positive.
times 9 is positive 36. So we get 9 times 4. That's our coefficient. X to the first, y to the second. Okay, and the last one. What's negative 2y cubed? Yeah?
Negative 8y.
Right. So this particular expansion alternates between positive and negative. That generally will happen when you have a minus in the original problem. Okay. Any question on that? So that's the binomial theorem. Gives us a quick way to expand binomials. Okay, we'll do this one real quick. So this one doesn't have a negative in it, but it's got a power to a power, so we just have to make sure we remember that rule. What's my first term going to be here? Same row in Pascal's triangle as the last problem. Yep.
2x cubed.
Yep, so it's 1 times 2x cubed. There's no minus, so everything will be added together this time. How about my second term? Elise, what's my second term? Yep.
3 times 2x squared
Yep.
plus.
No
I mean,
plus.
What, times y squared? Or no, times, wait. Times y squared?
Y squared to what power?
1.
1. Yep. Okay, next, let's do the next term. Kyle, what's my next one?
Three times 2x times y squared squared.
Yep. Y squared squared. And what about my last term? Yep.
Y squared cubed.
Y squared. And now that goes to the third power. So remember, power to a power, you multiply. So this is going to give us 2 cubed is 8x cubed times 1. It's going to give us 2 squared is 4 times 3 is 12. X squared, y squared. Nothing happens to the y squared this time because it's to the first. Okay, next one. 3 times 2 gives us 6. X, y to the fourth. And the last one, y cubed squared, y to the sixth. There we go. Okay, any question on that one? So generally, if they start to get a little more complicated, either because of a power to a power or because of subtraction, the exponent I usually make a little bit lower versus on a real simple one where there's nothing else going on except a single letter and a single letter, you probably see a higher exponent there. All right, so those problems were fine with Pascal's triangle because the power was small enough. But if the power starts to get really big, like even a simple one, a plus b to the 17th power, well, I can tell you all the letters, like a to the 17th, and then a to the 16th, b to the first, b to the 15th, b to the second. I can tell you all those, but all the numbers that are going to go in front of them, unless you know row 17 in Pascal's triangle, I haven't explained a different way to do it. And to generate row 17, that's going to take a long time. Okay. So we need to think about another way we can find the numbers in Pascal's triangle. And there is a way we can do it, and that's with something called factorials. Anybody remember factorials? Factorial though? Yep.
Is that like with an exclamation mark?
Yep, with an exclamation point. So, first of all, when we're dealing with factorials, we're only going to deal with integers. We don't talk about anything with decimals in factorials. Okay, it's all integers. And when you want to find what's called a factorial, you put an exclamation point after the variable. Okay, that's a symbol that means factorial. So in this case, if you wanted to find a factorial, what a factorial means is to multiply every number from your number all the way down to 1. So if you want to know what's 5 factorial, it means 5 times 4 times 3 times 2 times 1. Every single number from your number to every integer underneath it, you multiply together. And when you pronounce this, you say n, because there's an exclamation point. Versus just a regular variable, you would just say something like n. So there's n, and then there's n. So you remember, you get excited when you say it. Okay, so n is the product of every number from n down to 1. So 100 factorial would be a very big number. It would be 100 times 99 times 98, all the way down. Factorials get very big very quickly, and you can't even do some of them on the calculator. You could probably do 50 factorial. The button for factorial, I don't know if there's a key for it, but it's under math, probability, option 4. I know it's there. I don't see it on the keypad. Okay. This exponent can only go to 99. Once that hits 99, the calculator doesn't have the ability to do it. So somewhere, I think in like the 70s, it'll start to tell you that it's an error, overflow, because it's too big. So that's not even that big of a number, 78. Okay. But that's higher than what the calculator can do for factorials. But you should never have to type in something that big. So I'll show you what we can do if you had to do that, how you can make it smaller so the calculator can do it. So first one seems a little weird. How do you multiply every number from, so a factorial is multiplying every number from your number down to 1. How do you multiply every number from 0 down to 1? That doesn't even make sense. So what they do is for 0 factorial, they just define it to be 1. Okay, so 0 factorial is just 1. How about 1 factorial? If you multiply every number from 1 to 1 together, what would you get?
Is it also 1?
It would just be 1, yeah. Okay, so far it doesn't look like it's growing very fast. How about 2 factorial?
2.
That's 2. Okay, 3 factorial? That's 6. And 4 factorial? 24. 4 times 3 times 2 times 1. Yes, you don't need the times 1. And what about 5 factorial? Yep, 120. So it grows pretty fast. Now, we don't do decimal factorials. You can try typing it in. It gets a little different. So we're just going to talk about doing it with integers. So we're going to talk about how we can use factorials to find the numbers in Pascal's triangle. And generally, we're not finding an entire row. Okay, what I would ask you to do, if I wanted you to raise something to like the 17th power, I may ask you, what would the coefficient of the 13th term be? Okay, so I'm not asking you to find all 18 numbers in that row. I'm just going to ask you to find one of them. Because even with this formula that I'm about to show you, if you had to do all 18, it's going to take a while. So what we're going to do is we're going to use 2 letters to describe the position in the triangle that we want to find. The row is going to be letter N, and the column is going to be letter R. And the notation we're going to use looks like a set of parentheses with a number in the top and in the bottom. And this top number is your column, and the bottom number is your row. So if I wanted you to find something in, say, whoops, switch that. N is row, R is the column. Row, column. So if I wanted you to find something in row 8, column 5, that's the symbol that I would use. Row, column. That's row 8, column 5. The way that you generally see that pronounced is N choose R, and that comes from probability. Because if you had 8 objects and you wanted to know how many ways somebody could pick or choose 5 out of the 8 to take from you, that's the notation you use. 8 choose 5. Okay, so same concept as having 8 objects and asking how many ways you could pick 5 out of 8 as a group to take. Remember, the numbering always starts with zeros. Row 0, column 0. If you start with 1, everything's going to be off. So always start with 0. Okay, and we're not going to go through the proof of the formula. I'm just going to show you what the formula is to figure out any position in Pascal's triangle, as long as you know the row you're in and the column you're in. You have to know those 2 things. So that is the formula. It's n factorial over n minus r factorial times r factorial. And when you take, well, if you take statistics next year, you'll definitely see that formula. And you'll see it when you talk about combinations. All right, so now let's see if we can write Pascal's triangle using this notation. Okay. This is the row. That's the column. What would the number at the very, very top of the triangle, what position is that number in? Row what? Column what? Yep.
0, 0.
0, 0. That's the notation for the number at the very top. N is 0, R is 0. And if you fill in 0 for N and 0 for R, you'll get the value that's in the top of the triangle, which is a 1. Okay. Second row. Well, row 0. Now we're in row 1. What do you think the notation would be for the first number in the next row? Yep.
1 choose 0.
1 choose 0. Row 1, column 0. How about the next number in that row? What would be the notation for that one? Yep.
1 choose 1.
1 choose 1. Yep. Choose 1. Okay. How about the first number in the next row? What would be the notation for that? Yeah.
2 choose 0.
2 choose 0. And the next number? Yep.
2 choose 1.
2 choose 1. And the notation for the last number? Yep.
2 choose 2.
2 choose 2. Right? And we can write it out as long as we want, but that's the notation for it. So now if you want to find this value, plug in a 3 for n, top number is n, plug in a 2 for r into the formula up above, and you'll be able to figure out what that number is. 1, 3, 3. This comes out to a 3. That's 1, 3, 3, 1. So does it save any time for the first rows in the triangle? Not really. You can do the first 4 or 5 rows probably quicker than using the formula. But if we had to get to row like 78. And I said, what's the fifth number in row 78? You could find it very quickly. 78, choose 5. Just fill it into the formula. The only problem with that is I showed you when you plug in a number in the 70s for a factorial, the calculator can't do it. It gets too big. Well, we have a way that we can work around that. Okay, so I'll show you how we work around it. Okay, so here is the binomial theorem, now written with our new notation. So the very first coefficient would be from the row of your power, and it would be in the first column. So n, choose 0. That's the very first coefficient. Row n, column 0. Then the power on the a would be to the highest exponent, so it would be the a raised to the n. And we don't have a power on b yet. B doesn't come in until the next term. What do you think my next coefficient would be? Yep.
3?
Well, it's going to be something general. It's not going to be a specific value. Because we don't know. Maybe this is row 62. We don't know. We don't know what row we're in.
Is it n choose 1?
Yeah, whatever the next number is in row n. So it would be n choose 1. And now the a, what's going to happen to the exponent on the a? Yep.
N minus 1.
It goes down 1. So it's going to drop to an n minus 1. And then what's going to happen to the exponent on the b? Yep.
N plus 1?
No, not.
It's just gonna be 1.
Just going to be 1. This is the first time we've seen b. So it's just b to the first. How about my next, what's my next coefficient? Just the notation for it. Yep.
And choose 2.
And choose 2. Okay, so we got to figure out what n choose 2 is. Exponent on a goes down again, so now it's going to be minus 2. Exponent on b is going to go up. It's going to go to the second. Yeah, and we can continue this pattern as long as we want. Right? But eventually, we're going to get to the second to last column in Pascal's triangle. N choose n minus 1. That's the second to last column. So if you're looking at a specific row, you're right there now, right before the last one. The exponent on a is going to be the smallest it will ever be. A is all the way down now to a power of 1. It's about to disappear in the next term. The exponent on b is almost as big as it's ever going to be. It's 1 away from the biggest exponent that you're ever going to have. Okay. And then the very last term, so now we're here, this is row 1, 1, 1, 1, 2, 1. It's row 3. In the very last row, your coefficient is finally at the end. Row 3, column 3. Row 5, column 5. You're at the last number. The a is gone, and the b now has the highest power. Okay, so that's the pattern of the binomial theorem in general. Okay, the only problem we still have is what happens when n gets really big. We can't put it in on the calculator. Okay, so let's see how we do it. Okay, so we have 6 choose 4 and 9 choose 5. All right. In 6 choose 4, what's n? Yep. 6. That's my n. That's my r. Fill that into the formula. So 6 factorial over 6 minus 4 factorial. 6 minus 4 is 2. times r factorial is 4. Now, if we do this clever, there's a lot of things that are going to cancel out. In the top, you've got 6 times 5 times 4 times 3 times 2. That's the top. Now, don't worry about doing this one out yet. Just leave that. But do out the other one, 4 factorial. What do the top and the bottom both have in common? Yeah?
4 times 3 times 2.
4 times 3 times 2. The bigger factorial in the bottom will always completely cancel with the top. So that's gone. Now we've got a much easier problem. 6 times 5 over 2 times 1. 15. So if you look at Pascal's triangle and you go to row 6, column 4, the number should be a 15. I don't think I did out that many rows. Oh, I did. Row 6, column 4. 0, 1, 2, 3, 4. There's your 50. Let's try this one. 9 choose 5. So 9 factorial. And then in the bottom, what are we going to have there? Yep.
4 factorial times 5 factorial.
4 factorial, 5 factorial. And now in the top, everything from what number down is going to cancel out when you write out 9 factorial. Everything from, yep, 5 down is gone. So all you're really left with is still pretty big, but that's going to get a lot smaller. 9876, 5432 is gone. And in the bottom, 432. Everything in the bottom has to cancel with everything in the top. Factorials never come out to decimals. Well, 3 times 2 cancels that. And then 4 goes into 8 2 times. So we're left with 9 times 2 times 7. Well, 9 times, let's do that part first. What's 9 times 7 give me? Yep.
63.
And then when we double 63, we get, yep, 126. So a lot of times you can do the factorial in your head, or you can do it a lot easier by reducing it. Any question on that one? Okay. All right, so the last one, I'm just going to show you. When you expand something to the 15th power, how many terms do you get? Yep. 16. Let's pretend those are all the different terms. I'm not asking you to find all 16. That would take a long time. I'm asking you for one of them. I want to know the 12th. 0. Remember, you always start counting with 0. 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I want that one. Okay. So you're trying to find the 12th term. Okay, think about the coefficient first. This tells you the row. You're going to be in the 15th row of Pascal's triangle, and you need the 12th column. So you're going to have to figure out 15 choose 12. That's the number. Now we just have to think about the powers on the 2x and the 3y. 2x is going to have a power. 3y is going to have a power. What would be the power of 2x on the first term? Yep. 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3. So that's going to have a 2x to the third. And what would be the power on the 3y? We know there's a connection between these two exponents and that one. It has to be 3y to the has to be to the 12th because these have to add up to 15. So that's the answer. You got a little bit of work to do to simplify that. You got to figure this out and then write this as 8x cubed. So you got to do it out. But that's the idea. Okay, so I make those dashes. That's how I think about it. And just remember, you start with 0. If you don't start with 0, that'll mess you up. Okay. But we can look at one like that tomorrow before the test. Okay, so the homework is on page 606. It's just a lot of like short sections of problems. So it's 1, 3 to 8, 11 to 15, 17 to 19, and 21 to 25. Okay, so a reminder, I'll be after school today if anybody needs extra help. And we have our test tomorrow, and I will put the topics on the board.